So you've probably used ChatGPT, but have you ever stopped to wonder what's actually happening behind the screen when you type in a prompt? We're not just talking about the AI model. We're talking about the colossal, globe-spanning machine that serves it to the entire world. Okay, let's do this. We're going to go deep under the hood and explore the architecture of one of the largest AI services ever built.
Just to get a sense of the scale we're dealing with, let this number sink in for a second. ChatGPT is serving over 800 million active users every single month. This is not your typical website or app. This is a global utility, and it demands a completely new way of thinking about engineering.
And that really gets to the heart of the challenge. This quote nails it. ChatGPT marks a fundamental shift. See, most websites are stateless. They don't need to remember you from one click to the next. And their main problem is fetching data quickly. ChatGPT is the opposite. It's stateful. It absolutely has to remember your entire conversation, and it's compute-bound, which means the biggest bottleneck isn't a hard drive, it's the raw brute force processing power of its chips.
All right, so here's our game plan for deconstructing this beast. We'll kick things off with that new engineering paradigm. Then we'll look at the actual physical foundation, this multi-cloud setup. We'll see how it stores billions of conversations, trace the life of a single prompt from start to finish, peek inside the AI's brain, and finally, talk about what this all means for the future. So, what does this new paradigm really mean in practice? Well, in a traditional app, your biggest worry is getting data from a database fast enough. Here, the whole game is different. The main challenge is getting a user's request to a giant cluster of GPUs, having those GPUs perform literally trillions of calculations, and then streaming that answer back, all while perfectly remembering the context of the chat.
To solve that massive compute problem, you need one thing: GPUs. And not just a few, you need tons of them. So many, in fact, that you can't just rely on one cloud provider anymore. The demand is just too intense. This is where the physical infrastructure story really begins.
Now, this is where it gets really interesting from a strategy perspective. For a long time, everyone thought OpenAI was an exclusive Microsoft Azure shop. But to scale, they've had to make a huge pivot to a multi-cloud strategy. Think of Azure as the foundational backbone, but they're also tapping into AWS for its huge GPU farms, Google for its specialized AI chips, and even smaller specialized providers like Oracle and CoreWeave. It's all about resilience and getting every last drop of compute power they can find on the planet.
And the kind of investment this requires is just staggering. This number right here, $38 billion. That's just a single multi-year deal with Amazon Web Services. We're not talking about just renting a few servers. We're talking about funding the construction of some of the most powerful supercomputers ever built.
Okay, we've got the muscle, the raw compute power. But what about the memory? Where do you actually store all of these billions and billions of conversations? The data layer has to be ridiculously fast for looking things up, but also able to scale to an unimaginable size.
This is the million-dollar or maybe billion-dollar question for the data engineering team. Seriously, how do you build a system that can handle the constant flood of new messages coming in while also letting any one of its 800 million users pull up their entire chat history in the blink of an eye?
And the solution is really clever. It's a hybrid approach, kind of the best of both worlds. For the core stuff that doesn't change too often, like your user account and settings, they use a rock-solid traditional Postgres database. It has one main server for writing and almost 50 copies around the world for fast reading. But for the absolute fire hose of actual conversation data, they bring out the big guns. Azure Cosmos DB, a database specifically designed to grow sideways infinitely across the entire globe. And when I say fire hose, I am not exaggerating. Right after GPT-4 was launched, Cosmos DB was handling over 10.6 billion transactions per day. The incredible part is it just scaled up automatically. It added thousands of new partitions behind the scenes to handle that massive spike in traffic, and nobody even noticed. It just worked.
So what makes Cosmos DB the perfect tool for this job? Well, this table breaks it down. By using the user ID as the partition key, the database can automatically scale out as more people sign up. Its NoSQL document model is perfect for storing complex, nested chat histories. It has what's called 5 nines availability, which basically means your chat history is never, ever supposed to be unavailable. And that last one, vector search, that's the real secret sauce for making the model smarter by letting it search for relevant data.
Okay, so we've got the compute power and we've got the data storage. Now, let's make this all real. We're going to follow a single prompt, your prompt, from the exact moment you hit enter to the second the response starts appearing on your screen.
To make this complex journey a little easier to digest, let's use an analogy. Let's imagine the entire ChatGPT system is a hyper-efficient, futuristic restaurant. You've got a host at the front door, a very smart manager running the floor, a whole research team in the back library, and of course, a world-class chef in the kitchen.
Okay, here's the real technical play-by-play. First, your app, built in React, sends your request. It immediately hits the API gateway. That's our host stand, which checks your ID and your subscription level. Next, it's passed to a service called the Conversation Orchestrator. That's our manager. This part is crucial. It pulls up your past conversation for context and decides if it needs to use any special tools, like searching the web. Then it bundles everything up into a final order and sends it to the chef, the GPU cluster doing the inference. As the model generates words or tokens, they're immediately streamed back to your screen using a WebSocket. And finally, once it's all done, the whole exchange is saved back to the database for next time.
And here is the full tech stack, the complete list of ingredients that makes that whole journey possible. You've got React for the user interface. On the back end, it's mostly Python with a framework called Fast API, which is great for handling lots of requests at once. WebSockets are the key to that real-time streaming effect. And then you've got two different layers of orchestration. You can think of Kubernetes as the system that manages all the regular application services, while a more specialized framework called Ray is brought in to manage the incredibly complex workload of the AI models across thousands of GPUs.
So let's zoom in on that inference step, the absolute core of the entire system. This is where your prompt finally meets the AI model running on a massive fleet of GPUs. This is without a doubt the most computationally expensive and complex part of the whole process.
At the heart of that engine is the transformer. This is the neural network design that changed everything. Its key innovation is something called a self-attention mechanism. Basically, it lets the model look at all the words in your prompt at the same time and instantly figure out how important each one is in relation to all the others. That's what gives it such a powerful grasp of context and nuance.
But running these huge models at scale creates some really unique problems. This chart is absolutely fascinating. It shows you how the memory on a single GPU is used. Now, the model itself is huge, taking up 65% of the memory. But look at that other big piece. A full 30% is taken up by something called the KV cache. You can think of this as the model's short-term memory just for your specific conversation. And managing this cache for millions of simultaneous users is one of the single biggest challenges in all of AI infrastructure.
So, after taking this entire system apart, piece by piece, what are the big takeaways? What does this incredible architecture tell us about where AI services are headed in the future? When you boil it all down, this architecture works so well for three main reasons. First, performance. Clever tricks like caching and streaming tokens make it feel incredibly fast. Second, quality. It uses tools and data retrieval to ground the model in reality, which helps keep it from just making stuff up. And finally, reliability. The whole modular, multi-cloud design means that one component failing won't bring the whole thing crashing down. Every piece can scale and fail on its own.
And that leaves us with one last, pretty big question to chew on. What we've just walked through is an unbelievably complex system, all designed to orchestrate a simple conversation. But as these AI models get more powerful and start to become autonomous agents that can complete complex tasks, is what we're really looking at the beginning of something much, much bigger. Is the next great engineering challenge of our time to build the world's first true operating system for intelligence itself,